I think I'm just going to start with telling you what generally sine, cosine, and tangent look like. I want you to take notes on this. Slide your, get to a margin where you can write or add a page. And this is generally what sine looks like. This is just kind of generally how it looks. And it just keeps going. And it just keeps going and going and going in both directions. But note how it starts at 0, 0. It goes through 0, 0. So sine starts at 0. Okay, cosine, I'll do, let's just do this. New graph, just put it right underneath it because it's going to look a lot alike. Cosine, it looks exactly alike. It's just that it starts at 1 and then it does that same wave thing. So do you get that sine and cosine are pretty much the same thing? It's just one of them's, think of it as sine is the one that it starts with. It is, actually. If you think about this, sine is the only one there is. Because cosine is just sine shifted over. That's all it is. Cosine is not original. Sine is the original. In fact, when you write equations for these things, they're called sinusoidals because they're all based on sine. Okay, so cosine is just sine except shifted. And tangent, the last one, tangent is sine over cosine. So sine is the original. Cosine is just a copy of sine except shifted over. And tangent is sine over cosine, which means that you really only needed sine. So technically on your calculator, you could just have the sine button if you knew how to do it, right? Because cosine, you just take all your sine answers, shift them over. And tangent, you could always just figure out the sine, then figure out the cosine, and then divide them, because that's what tangent is, sine over cosine. Okay, so here's what tangent looks like, though. When you divide those two weird curves by each other, you get this. Tangent, much completely different. It's like, you might even think it's a wave, but it's not. Okay, and it's got places where it doesn't exist. Why? Why all of a sudden does tangent have spots that don't work? Remember? Whenever cosine is 0, like right there, wherever cosine is 0, well, wait, that's not a place where cosine is 0, my bad. Cosine is 0 right here, and right here, for instance. Those are these two spots. Because wherever cosine is 0, tangent can't exist. All right, so that's what the three graphs look like. Two of them are waves. The third one is a weird looking, kind of looks like an x to the third graph. You know, y equals x to the third. It's not the same thing, but they look similar. Okay. So there's just this overview of what sine, cosine, and tangent kind of look like. Now let's specific. Get to this page. So we're going to do a really nice one here. So remember where sine started? What did sine do that the other one didn't? 0. You start here at 0. And then it goes up and down. Guess how far up and down it goes? What do you think the highest that sine ever goes is? Do you remember that from this? Okay, this point right here is what comma what? 0 comma 1. And what's the sign? Is the sign the x or is the sign the y? Sign is the y. Do you get that 1 is the y and the highest that the y ever will go is 1? So the highest that this wave ever goes is 1. All right, so it goes up to 1 at pi over 2. In fact, look at that. It's pi over 2. That's pi over 2, and it's 1. This is pi. What's that spot? What comma what? negative 1 comma 0, okay? And sine is the y, and so what's the sine of pi? Sine is the y, so what's the sine of pi? 0. Pick another dot over there. See, we're just picking up little spots. I should have started with this one, really. That's where sine of 0 was. And that was at 1 comma 0. And the sine is the y, and so it was 0. So it went to 0. Here, to 0. Then I went to 1. And then I went back to 0. What do you think's going to happen down here? Well, let's figure it out. This is 3 pi over 2. And what's the point that's right there? What comma what? 0 comma negative 1. Okay. And what's the sine? It's the y. So it's negative 1. So that's how you build the exact points. And what's 2 pi exactly? 2 pi is the same exact thing as 0. And so it's back to 0 again. So that's why sine looks like that. Now there are 5 key points. I'm going to put a blue dot, or a red dot at all of them. That's one of them. That's the second one. That's the third one. That's the fourth one. And that's the fifth one. Those are the key spots. You also have to have labels here at pi over 2, pi, 3 pi over 2, and 2 pi. You also have to have a label here at negative 1 and 1. So that's kind of complicated. You'll get used to it. By the end of this unit, you'll have probably done that 25 times. That same exact setup. Pi over 2, pi, 3 pi over 2, and 2 pi. All right, there's a few names you need to know about these. This is how long it took it to complete a whole cycle. And that is called its period, and that is 2 pi. For sine and cosine, their period, the time it takes to complete a full cycle. Like, it isn't back to where it started until 2 pi. Cosine is going to be the same. It'll also have a period of 2 pi. It takes 2 pi time to get a full cycle over with. And then there's one more thing that's important, and that's this, and that's called the amplitude. And that's how high does it go? Okay, picture a wavy lake. Can you picture waves on a lake? And then imagine that you could hold up your hand and say, stop. And all the water just went to flat. Do you get that this would be the water line? If all the waves just went. Okay, so then how tall was the wave really? Was it really from negative 1 to 1? No, the waves actually, technically, when you measure wave height, it's compared to flat water, completely calm lake. The waves were going how high above the normal water line? See what I mean? So that's what amplitude is. So really common for kids to think the amplitude is 2. Because they think, well, it's the up and then it's the down. Nope. It's just from flat water, like if this was a wavy lake, going to completely flat. And then it went, how high were they going? Well, they were going once. The amplitude of this thing is 1. The period is 2 pi. Amplitude was 1. Let's see. I think that's pretty much it. Tadros.
Do you have a negative amplitude?
Nope. Amplitude is a height, and you can't have a negative height. So no, it's an absolute value of, if you ever think you got a negative number, just absolute value it, and it'll be that. Yes?
Wouldn't the period just be pi since it's vector extended when it's the pi?
But has it completed the full cycle? No. Otherwise, if the period was pi, then sine would actually look like this. It would do this, and then it would just do it again, and then it would do it again, and then it would do it again. See what I mean? So no, the period is 2 pi. All right. Let's go to this one. I think you get that the setup is exactly the same. The 5 key spots, I feel like there's 4, but 0, 0 is a key spot, right? So that's spot 0. So there's 5 key spots. And do you remember what this one starts at? Yes. Right there. It starts there. And now, instead of recreating all these dots and saying cosine is the x, cosine is the x, cosine is the x, I could do that, but I think that'd be boring. So I'm just going to draw it and make you think about where would it end its complete cycle? Let's say it a little louder. It'll end at 1 again. That's correct. It started at 1, it has to end at 1. So right there at 2 pi, it's going to end at 1. But you know this thing looks like a wave, right? So then halfway through, it must be at its low point, right at pi. Does that make sense to you? Halfway through it, it's got to be all the way to the bottom. Because it has to cycle back and forth between -1 and 1. All right, so then I like to make this in 4 parts. Here's the first part. Here's the second part. Here's the third part. And I'll leave the last part black. All right, I see a few cell phones out on desks. So you could put them down, away, backpack. I know. A lot of times it's because your pockets are uncomfortable. It's fine. Just don't have it in your pocket. Don't have it in your lap either. Just put it in the backpack. All right, so that is a typical test question. But, man, if we were going to make you just graph sine or cosine, that'd be pretty easy. Because, of course, this is honors pre-calc. And that would be more like that's pretty basic. So what do we typically do to make these harder? Well, typically they're going to look like this. 2 cosine of 3x. Then we got to remember things like, what does that do to something if you put a 2 in front of it? Yeah? Vertical stretch. So the thing gets twice as tall and goes twice as low. See what I mean? Okay. What about a number on the inside? Do you remember something about the inside? I was just talking to my friend that was in prison. Yeah, you don't trust it. You don't think, oh, it's going to get 3 times wider. It's the opposite. It gets 3 times narrower. Now, that's hard to do on drawing. And so good news for you, we don't make you go through and redraw this 3 times narrower as it was. You could do it, but man, those are hard to do. So instead, what we allow you to do is you take this number here. And remember, if we trusted it, we would just times all of these by 3. We don't trust it, so we don't just times them all by 3. What do you think we do? Divide by 3. Exactly. So 2 pi over 3. How the heck do you take pi over 2, this guy here, or 3 pi over 2, sorry, and divide it by 3? What's faster than dividing by 3? Multiplying by 1/3. So this ends up coming out to 3 pi over 6. Ooh, I know that one. 3 pi over 6. That's pi over 2. I can just reduce it. Okay? And then this one, I can divide by 3. So anytime you can just divide by 3, do it. But then this one is not going to divide by 3 real nice, so I'm going to times it by 1/3. Do you get this number here is kind of tricky because you have to renumber the whole x-axis. All right. Now, another thing we will let you do, instead of having to redraw the graph twice as tall, is instead of saying it's twice as tall, you put a 2 here and you put a 2 here. All right, -2 down there. There. I've just changed this to graphing 2 cosine of 3x, and that is a typical question. By doing what? By changing the x and the y axes. This came from this. And this made me divide everything by 3. Okay. I know that was intense. So I want you to just make a quick graph of sine right there. Because this will help you remember what I just told you. Because me telling you, 10%. That's all you get. You have it in your short-term memory right now. So you got most of what I said. But a day from now, you're gonna have 10% of what I said. But by doing this right now, remember something like 6 times as much. So I know you're like, well, it's a wave, it goes like this. Okay, yeah, but you got to label the 5 spots. Plus how high and low it went. So really there's 7 spots that have to be labeled on every graph. So, but do I really make you label 0, 0? No, it just makes it kind of messy. So, pro tip on labeling. If I were you, I'd always start with the 2 pi and then keep cutting things in half. Because what's half of 2 pi? Because right here is half of 2 pi. It's pi. What's halfway to 0? Well, that's pi over 2. And then you just kind of missed 1. And then I would count them back up and go 1 pi over 2, 2 pi over 2. That spot must be 3 pi over 2. That's the hardest one to remember. And it goes as high as 1 and -1. Any questions about graphing sine? Do you get cosine? Should be easy if you know sine. Because you have all the same exact labels on the x and the y axis. 6 numbers to write in. 7 if you count 0, 0. But cosine is just going to start its wave in a different spot. All right, without me blabbering anymore, I'm going to pause for a second. Please graph and label all the 7 important spots, or 6, I guess, if you don't count 0, 0, for cosine. So I'm starting right here. And then what's the most important of these marks? Well, that's kind of a judgment call. But I like to start at 2 pi. And then I like to go to half of that, which is pi. And then can you fill in the other ones for me?
Pi over 2 and then 3 pi over 2.
Pi over 2 and 3 pi over 2. Good. And then these spots, how high and how low?
For pi over 2, it's 0, or yeah, 0, 1, or yeah, just,
Okay, what I guess I was asking is what do I put here and what do I put there?
oh, -1 at the bottom and then
Okay, good. And now I'm going to continue. I'd like to do this in 4 parts. And then this next part, I go like this. And this next part, I go like this. And then the last part, I go like that. There. It's kind of a valley. Do you get it? Would keep going in both directions? So we really only graph these between 0 and 2 pi. Another way we could say that is we only make you do 1 period of the graph. Because otherwise it would keep going in both directions forever. Okay. Why would it keep going in both directions forever? Because you remember the circle thing that we did before? Do you get you can keep going around and say, hey, I want to do 90 times 5 is 450 degrees. You can do that, and it's just going to be cycling back to old ones you did before. If you go around again, you'll get another answer you got before. And if you keep going around, you can keep going around forever and keep getting those same answers over and over and over again. So it's that cycle of around and around that's being replicated when you keep going here. It'll just keep recycling the same answers over and over. Okay. So the hardest part is the part where and this is actually another set of notes. So why don't you take just a second, go into the notes, find the next set of notes. This is where we describe the official, how you stretch these things and how you shrink these things and how you shift them. It's called a phase shift. That's like a shift to the right or the left. So get to these notes. They're in Schoology. It looks a lot alike. Understood? Understood. Okay, so the amplitude here is that's changing how high the thing goes. That would be like a stretch. The period that's saying that number on the inside changes the period. And phase shift also about, yeah, I'll show you. It's also about the inside. But if there's two things you can do on the inside. So let me go back to parabolas. I think most of you guys fondly remember the good old days when things were as simple as, oh, it's just a parabola and it's been shifted where? Right 3, okay? Well, this is just like that, except now it's y equals sine of x minus 3. And take a guess what that does. Shifts it right 3. But usually, since our x-axis is numbered in radians, it's usually like that. And that would mean take the whole graph and shift it to the right, pi over 2. So you'd take the graph we just made, and you'd just take every point on it and move it over to the right. And it would kind of look like, say here's where normal sine was. Sine starts at 0, right? And that would make it move over to the right, and it's like I dragged it over and made it start here instead. See how the blue one is kind of just dragged to the right? Okay, so that's what that looks like. That's a shift to the right. Do you get how that's different than scrunching it down and making it finish faster? Like that green one, that's like sine, except you made it finish itself off, like, you know, like it finished the complete cycle way faster. That would be like putting a number here. Would that make it get wider or narrower? Narrower. So would we multiply all the numbers by 2 or divide them all by 2? Divide them all by 2. You don't trust it. Seems like multiply them all by 2, but you don't. So then you would take all these numbers here, and you would have divided them all by whatever's here. Okay, we're going to move on to a typical question. Let's say that they tell you A is 2, B is 3, C is pi over 2, and D is 1. Those are considered A, B, C, and D. Take a wild guess from the letter what A represents, the what of the function. Yes, amplitude. Everybody write that down. B, does B seem like a shift to you? No. Does C seem like a shift to you? Yep. That is called the phase shift. How about D? Where does D move? Up. If we had subtracted 1, would it move down? Okay, so this is up or down, and that's all I want to call it, up or down. I could give it a fancy name. A vertical translation. But come on, it's moving up or down. And B, what is that? Well, is it vertical? The B? No, it's horizontal. Okay. And is it a shift? No. So it must be a horizontal what? It's a shrink. Good. Can it be a stretch? Yeah, it can be a stretch. All right, cool. So if they give you this, you can go, amplitude's 3. Did that affect how tall or how wide it was? How tall. So instead of going to 1 and -1, now it's going to go to 3 and -3. It's that simple. And what were those 4 key spots, or 5 if you count 0, 0? Well, always put them on there. I'm telling you, don't try to like change them in your head. Always do them the same. I always cut in half and go 2 pi pi, pi over 2. And then I go back and go, okay, 1 pi over 2, 2 pi over 2, 3 pi over 2. There. But are we going to have to change it? Yeah, just deal with it after you've written the original ones. Okay? So I got my originals down. Now what am I going to do with the 4? Divide them all by 4. Well, this divides by 4 easy, and this divides by 4 easy, but the other two you don't actually want to divide by 4. You want to times by 1/4. So I put a 4 times down here. 4 times 2 makes 8, so that's 3 pi over 8. And 4 times 2 makes 8, so that's pi over 8. So pi over 8, pi over 4, 3 pi over 8, and 2 pi over 4, which reduces to pi over 2. And then, if you just know what cosine looks like, it's a valley. I like to do it in 4 parts. I like to go actually halfway through and put a dot there, because then I know I'm kind of heading towards that dot. Oh, this is sine. I saw cosine right here, and it made me think cosine. You're right, it's a sine problem. So I don't start at 1. What do I start at for sine? 0, 0. Okay, sorry. Sine starts here, ends here, high spots here, low spots here, and then you can kind of make it, there you go. As long as you're labeled well, and you have the general shape of the graph, I'm not the guy who's going to say, that went a little too low there. It's labeled, right? It's 3 pi over, well, this is a 4 times 2. I wrote over it too many times, but that's 3 pi over 8. So as long as you got the labels right, and you got generally the curve in the right general place, you're good. Okay, so what's one thing I haven't talked about? What's one other type of thing you can do to a parabola that I haven't talked about yet? A flip. Where would I put the negative? Hint, we will never put one on the inside. So you could put a negative right there. And do you get that would take the whole thing and flip it upside down? So wherever the wave was at its peak, it would be down in its valley. So I'm going to rewrite this one with the green and say it would be like this then. If you had a negative in front, it would do that. All right. Now the good news is, I know that was a lot, but all we do tomorrow is practice these. Okay, so sine, cosine, and all kinds of changes on them. All right? I'm going to give you a couple problems that I want you to try right now. And this is just a little too intense for a first question, so we're not going to shift it. We're going to scribble this out. Everybody, please scribble that out on the flamingo page. It has a negative at the front. My advice to you is wait till the very end. You're all done. And then just flip your graph over. So always start with the original. So if this is cosine, it would generally look like that. Always start with your original graph. So if I were you, I'd act like I told you to just graph me cosine. Just graph cosine for me. And do that and label it with everything. And then go do the changes to it. Okay? So start by just graphing classic cosine first. Then do all these changes. Now, while we're working on that, I'm going to hand back your tests, and I'm going to pause the video here, and then we'll write in the answer in a sec. All right, so here's how you should have started. Start with cosine, and it goes from 1 to -1. And you might feel like you're wasting time labeling these. You're not. If you graph the original one and label it correctly, it's so much easier to just go through and change all those labels than to try to think up what they would be in this new graph. So telling you, please, 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 for your own good, graph the original one. Then go through and make the changes. So for instance, here, Since there's a 2 here, I'm going to change this to 2, a negative 2. Next, since there's a 2 here, I'm going to make all of these numbers get divided by 2. Or if they can't divide by 2 nicely, multiplied by 1/2. And yeah, you should clean these up. Pi over 4, pi over 2, 3 pi over 4, and pi. Okay, now, at this point, I would have had to cry and mark it wrong because, the kid forgot one last thing. That negative in front. So that was the one where it flipped it over. And there, the blue one is your final answer. Now, if this had been like the original, if I hadn't had you scribble this out, it would have just been a little too hard because that's a lot of things. But could we ask you to do that? Yeah, on a test. So what would you do? I'm going to erase this now and reveal. We would have shifted it to the right. You remember, it's always opposite of what you'd think. So that negative there means to the right. And I just realized something. This is powerful. It would not go to the right pi. And I know you're thinking it would, but it's because we have to factor out this 2, and this turns into 2 parentheses theta minus something. And that's why it's really important to factor that 2 out. Now why? Because the order matters. You better process this. That's the phase shift right there. You would move it to the right pi over 2. You remember my old saying, if you can factor it, you should? It applies again. Right here. That 2 can get factored out. And notice I had to put a divide by 2 there. So when I multiply this out, I get 2 pi minus 2 pi over 2, which is pi. Then that's the phase shift right here. Right pi over 2. So I'd go down here, grab the blue graph, and I'd move it to the right pi over 2. How far is pi over 2? That's how far pi over 2 is. You have to renumber it first, and then you move it that direction. So you have to always do your renumbering first. And then if you had to shift it, this is why I didn't do this on the first problem. Because holy cow, that's a ton of stuff. By the end of tomorrow, though, you got to be able to handle that. So this would shift over that far. So the blue graph now gets shifted over, and I'm going to make it green now. And it starts here. And its peak goes over 2 marks. And there. The green one, I know it's very faint. In fact, I better make it black. I'll make it a dotted black line. There, it's been shifted over pi over 2. Generally, kids do pretty well on this unit, but there's exceptions to every rule. So the people that aren't careful, if you generally make lots of little dumb mistakes on tests, man, there's a lot of chances to make dumb mistakes here. So you want to go through them at the end and go, did I remember to flip it? Did I remember to make it go twice as high? Did I remember to renumber all my numbers by 2, like divide them all by 2? And did I remember to shift it? And did I remember to factor it out before I shifted it? That's called the phase shift. And if you can factor it on the inside, you should. Let's make sure you really got that. Let's say it was just sine of 3 theta minus pi over 9. So first of all, this part doesn't change really anything. You always still go through and multiply everything by 3. No, divide everything by 3. So you'd have all your numbers across the bottom, which would normally have been pi over 2, 2 pi over 2, 3 pi over 2, and 2 pi. And you'd go through and multiply them all by 1/3 or divide them by 3. Okay? And then, can you factor that? Because if you can factor it, you should. I know you know it isn't just pi over 9, but I know you know it's related to pi over 9. What is it? Well, just try something. If you know it's related to pi over 9, maybe you go like, well, maybe I should times the top by 3. You'd quickly realize that when you multiplied this back out, if you multiply the top by 3, it doesn't work. You got to multiply the bottom by 3. So to factor that out properly, this becomes 9 times 3, it becomes 27. Then when you multiply this out, 3 times pi makes 3 pi. And 3 times the negative pi over 27 turns into negative pi over 9. And then that's how far you have to move it? Yes. Annoyingly, yes. You wouldn't have to win that hard on the test, but get used to factoring things like this. I think it's time to start the homework. This one's kind of above over the top. It's got too many changes to it. Yeah, it's plenty. So let's just get to the homework worksheet. So everybody, please, right now, open up the homework worksheet, and would you read me the first question on it? Did somebody already have it open? Save us some time.
Yeah, graph the trig functions.
Okay, can you read me the first problem we actually have to graph?
Y equals sin x.
Oh, that ought to be pretty easy. In fact, that's a little too easy. Everybody go ahead and do sine. Does it ask you to graph cosine next, I suppose?
Yeah.
You can cross off cosine. I'm fine with you. If you know that cosine is just going to start at 1, that might be just too easy for you. Okay, so if it's not too easy, if you're like, I could barely do this stuff, then graph cosine. But everybody should graph sine. You should at least graph one of them. Let's do this problem together.
Mr. Server, at the top it says graph the trig functions and then parentheses -2 pi, comma 2 pi. Wouldn't that change the
Okay, that's saying that they want, and I'm going to overrule that. They wanted you to graph it all the way to this direction too and do it twice. If you had to do that on a test, I would just graph your sine and go like this and get that all done and labeled and everything. And then I'd just continue it. See how fast that was? Okay, so it's really not that hard to do, but I'm not going to make you do this extra part. Okay, so there's sine, and you should have known it was 1, -1, and this is 2 pi, and this is pi, and this is pi over 2, and this is 3 pi over 2. All right. We established that problem 2 was to do cosine. What's the next thing they want you to graph, Robbie?
What?
What's the third question?
Y equals 4 sine pi x.
Okay. Let's do that one. First, please, always graph the original. Don't try to change these until after the original's done. After you've graphed classic sine, then go through and change the labels on these axes and you'll have it. We're doing the second problem of the worksheet for today. It is not at the end of the notes. It's in a separate file that's got a Dropbox, so you can Dropbox it when you're done. All right, I'm going to pause for a second to give you a chance to graph that, and then after you've graphed the classic sine, then go through and change it, and then check with the kid next to you. And now I'm going to hand those tests back.